Fourier transforms, chapter 8. So chapter 8 is the last topic we do in this course. And the idea behind this chapter is very easily explained. So instead of looking at intervals from minus L to L or intervals from 0 to L, we are now looking at infinity. So we look at intervals from minus to plus infinity, or we are looking at intervals from 0 to infinity, so a half infinite domain. Okay? And then what happens, I tell you right away, because whatever is the sum in the previous, which we did in the series expansions, this becomes an integral. An integral from minus to infinity to plus infinity, or in the other case from 0 to infinity. Okay, and then whenever we had like something like a Fourier series, well, guess what? This becomes an integral. And you see I used capital letters for the coefficients a omega and b omega, just to make sure that these are not confused with the little a and b n, so they're not quite the same, but they are very closely related. In fact, this formula which I wrote down here is called the Fourier Integral formula, and this is what I'm going to do today in this video. So that's section 8.11, Fourier Integral representation. There's one condition we need, which is that the integral over the absolute value of f is bounded. We call this often the finite mass condition. It just means if you integrate over the entire function, then you get a finite value. Okay. There are two technical conditions. Both f and f prime are piecewise continuous on every finite subinterval minus a to a. So, and then here is the essence of it. So what I like to try to do is to write f as an integral from 0 to infinity with coefficients a omega, which multiply cosine omega x, coefficients b omega, which multiply sine omega x. And I can compute the a's and the b's very similar as for the Fourier series. So here are the Fourier integral coefficient formulas for a omega, which is an f integrated with the cosine, and the b is f integrated with the sine, and of course there's a coefficient in front, which is 1 over pi. To get this formula, we make a little trick. So what we have, let me try this a little bit here. So we have minus to plus infinity, and we have a function, maybe something like this, which has a finite integral. So what I do now is I define a minus a and an a. Okay, so we need maybe a 0 here. And I cut the function off at minus a and a. And on this bounded interval, I can do my Fourier series right here. Okay, so in the interval minus a to a, I can write down a Fourier series. And I wrote it down here. I have a coefficient a0, which is then given with this formula here, 1 over 2a integral minus a to a f of x dx. I have the coefficients an, which are the cosine coefficients. The coefficients bn, which are the sine coefficients. So these are formulas you know so well. And then, of course, I send this a to infinity, and I send the minus a to minus infinity. And I hope I get a useful formula from this procedure. To do this, it makes sense to introduce a new term. I call omega n this here without the x. So this typical factor which arises all the time, n pi divided by a, I call this omega n. Actually, you know what? We should have done this early in the book, because we are writing down n pi x over l or n pi x over a all the time. Actually, I should have called it omega n on page 2. Anyways, so now we call it omega n, also here. And then we rewrite the coefficient. So the coefficient an, I rescale with pi divided by a, and then I give it the function capital A of omega n, and for the bn as well. And I do this, of course, so that in the end I keep the capital A and the capital B. So this will be the right a's and the right b's. For now it is just rewriting the an and bn just a little bit. Now let's look at the formula for bn. Okay. So we have integral of f sine of omega nx, so this matches already. And the factor in front, for the bn it is 1 over a, and for the capital B of omega n it is 1 over pi. And so this is exactly the transformation factor pi over a, which we have included there. Okay, so these are the same formulas. Now I use my Fourier series on the finite interval minus a to a, but now I write it with the transform coefficients big A and big B, and they have the wrong factors in front, right? There's a factor now of pi divided by a, which I need to make up for. So now the pi divided by a I call delta omega n, because it turns out to be the difference of n plus 1 pi divided by a minus n pi divided by a, okay? So the difference is exactly pi over a. So that is the delta omega n right there. And now I can let a go to infinity, because this means delta omega n, which is pi divided by a, goes to what? 0. And so we have a Riemann sum. Remember, somewhere in calculus we talked about Riemann sums. So this is a Riemann sum. So it has a limit. It has a limit, and then the sum becomes an integral, and that's that. So my Riemann sum is down here. You see, we got the integral, we got the coefficients, the a's and the b's. A's multiply the cosine, b's multiply the sine. Perfect. But hold on. There's one term too many. Here is the a0 term. I didn't talk about the a0 term. So this happened right in this formula. a0 is 1 over 2a integral from minus a to a f of x dx, which I can then extend to minus infinity plus infinity here in the integral, which I know integrates to m. So this is bounded by m. Here we use the finite mass. Okay, and I keep a 1 over 2a, so then this guy goes to 0 as a goes to infinity. Okay, so the first coefficient a0 actually is unimportant if you go to the limit. Yeah, and then we do get the full Fourier integral representation of f, written here, where the coefficients a of omega and b of omega are given as cosine or sine integrals of f. Exactly as I promised, right? So the sum is replaced by the integrals. Otherwise, the idea is the very same one. The coefficients, though, here in big A and big B are different. We had 1 over A for the Fourier series. Now we have 1 over pi for the integral version. If you have jumps, guess what? You jump to the half value. That's the same as for the series. So then here in formula 8.4, we write this down. So f from the right plus f from the left divided by 2, that's the mean value if there's a jump, equals the Fourier integral representation. No surprise here as well. Let's do an example here. So we have the function f of x is 1 for x less than 1 and 0 for x bigger than 1. So we have a jump at x is equal to 1, and at this jump we say f is 1/2. So let's plot this quickly. Here is minus 1 and here is plus 1, and so inside the function is 1 and outside the function is 0, and then here we say that it should jump to a half right here and here. It's a function which has a jump, but the full integral under the curve would be just this bit here, which is of course bounded. Actually the integral is equal to 2. Oh, cool. Here I have the function plotted again. Wonderful. So, yeah, here I said already, if I integrate the function, then I get the number 2. So we have a bounded mass, or we have a finite mass, so that's fine. So we can just go and compute the coefficients. So the coefficient a omega by the formula is 1 over pi, integral from minus to plus infinity, f integrated with the cosine. Now f is only 1 between the limits minus 1 and 1. So then we can replace that. And so we integrate just the cosine between minus 1 and 1. Cosine omega x integrated is sine omega x divided by omega between 1 and minus 1. So we can sub it in, and then we get something like sine omega minus sine of minus omega. Okay, and then the sine carries the minus sign to the front, so we get it twice. So this gets a 2 here. So we get 2 over pi sine omega over omega. Now for the b's, we integrate f with the sine function. So the same thing, the integral boundaries change. We integrate sine, which gives minus cosine divided by omega. We sub in 1 and minus 1, and we get 0, because here we have cosine omega minus cosine of minus omega, which then is equal to 0. Collecting this coefficient a in the integral formula, this is the a omega, then we get this formula for f. Isn't that cool? And we can even do this backwards. We can now say that this integral equals actually pi over 2 when x is between 0 and 1, pi quarters if x is 1, and 0 if x is bigger than 1. In particular when x is 0. When x is 0, right, you get integral from 0 to infinity, sine omega, cosine 0 is 1, so we divide by omega, d omega, and in the case x is 0, this is equal to pi over 2. So now all of a sudden we can integrate sine omega divided by omega, d omega, which is pi over 2. We get this basically for free.